To connect Turing machines to formal languages, suppose our tape begins with an empty square blank, followed by some string. If we let the Turing machine run, it may eventually change its state to the halt state. In that case, we say the Turing machine halts on input X. Notationally, our Turing machine is in its initial state with tape blank X, and we eventually derive a Turing machine in state H and something on the tape. We say the Turing machine has accepted the string X, and the language accepted by the Turing machine is the set of strings it accepts. For example, let's consider a Turing machine with the following transition rules, and let's see if this Turing machine accepts the input 111 blank 1. So we'll prepend our string with a blank space and initialize our Turing machine in state Q0 with the tape head on the blank space. So we start in state Q0 and read a blank space, so we move right. And since no state change is specified, we remain in state Q0, and since no symbol is printed, that initial symbol remains blank. Now we're in state Q0, and the current symbol is 1. So we change state to Q1 and move right, but again, since no symbol is printed, the tape doesn't change. We're in state Q1, and the current symbol is 1. We move right, don't change the state, and don't change the symbol. We do this a few more times until we eventually end up in state Q1 with current symbol blank. We move right, change state to Q2, but leave the current symbol. Now we're in state Q2 and read 1. We print blank, which overwrites the current symbol. And we also change to state Q3, and we also move right. But that was the last symbol. So what do we do? In general, remember we assume the tape is infinite in length, so there's any number of blank symbols after. So the next symbol is blank. And that means we're now in state Q3, and we read blank, and so we change into the halt state, and we don't change anything else. So the Turing machine accepts our string. What if we consider a slightly different input? We find the first few moves. Eventually we get to state Q3 and symbol 1, so we move right and change to state Q4. Again, even though we're at the end of the string, there are blanks beyond it, so there's still a symbol blank at the tape head. But there are no instructions for what to do if the state is Q4 and the symbol is blank. So the Turing machine crashes at this point. Now, how should we interpret the crash? Since the Turing machine has crashed, it will not process any more inputs, so it can never reach the halt state. So we should regard the Turing machine as having rejected the string. Now, the preceding, the Turing machine rejected the string because it couldn't reach the halt state. But for reasons that will become apparent, we might want a more definitive rejection. So some descriptions of Turing machines allow for multiple halt states. A halt state HA where the string is definitely accepted, and a halt state HR where the string is definitely rejected. The two are actually equivalent, since a Turing machine crash corresponds to an undefined transition, but if we wanted, we could define this as a transition into the rejection state. The main difference is whether we want our transition function to be defined for all inputs. And the reason that this could be important is let's consider the same Turing machine, but this time on the input 1, 1, 1. We'll prepend the string with a blank and put our Turing machine into state Q0 with the tape head at the blank. We'll find the first few moves. Now the Turing machine is in state Q1 and reads a 1, so the tape head moves right. Since the tape is infinite, there are blank symbols after that last 1. So the TM is in state Q1 and reads a blank, so it moves right and changes to state Q2. And since the tape is infinite, the next symbol over is blank. So now the machine is in state Q2 and reads a blank, so it moves right and switches to state Q1. Note that we're back in the same configuration we were 2 steps back, state Q1 and symbol blank. So the Turing machine will cycle at this point. And this means that our Turing machine never halts. This last example shows there's a subtle distinction to be made. Given any string x, a Turing machine could either reach the halt state, accepting the string, crash, or if we defined it, reach the rejecting state, rejecting our string. But there's a third possibility. The Turing machine could run forever, neither accepting nor rejecting x. We'll ignore this possibility for now, but whether or not a Turing machine halts leads to one of the most important problems in computer science.